All right, where were we last time? 21 was this day 12? It's this, no, day 11. 9K elixir. And we are hitting 5.4 and 5.5 today. As a quick reminder of what we've had so far, well, I'll do a recap when we have all the formulas in just a second. So 5.3, we did independent events. 5.4 is on dependent events. That was last week. And this occurs when the outcome of one event affects the outcome of another event. And just a quick scenario to make it like flesh it out in your head what I'm talking about. Let's say I draw the 7 of diamonds from the deck. I had a 13 out of 52 chance of drawing a diamond. If I draw a second card without putting the first card back, probability of getting a diamond is not 13 out of 15. It's not 13 out of 52. It is 13 minus 1. We already drew one diamond out. Over 52 minus 1. There's one less card in the deck. It's 12 out of 51 now. The probability has changed. The outcome of drawing one diamond has affected the probability of drawing a second diamond. It's actually affected the probability of drawing any specific card because the new total number of cards in the deck is 51. There's no longer the 7 of diamonds in the deck. So this is what this is kind of saying, in other words, is the probability of drawing a second diamond given that the first card was a diamond is The notation we put is probability, the second outcome, and then we do the vertical bar, and then we do the first outcome. Here, from our problem, it would be the probability that the second card equals a diamond slash first card equals a diamond. And the general notation they use for it is they say F slash E, which is probability of F given E. They'll say F given E. So this is the probability that F happens given or assuming that E has already occurred. There's a formula for this. Probability of F given E equals the probability of F and E divided by the probability of E. This is if you're using the probabilities, or if these are probabilities. If you have the number of outcomes and not listed as a probability, not calculated as a probability, I actually think it's a little bit easier. It's the same formula on almost word for word. And we did this in the other section when we talked about probability in general. We do N of F and E over N of E, where N means number of outcomes. We'll look at examples and we'll do them both ways, but I think that second way is easier, as you'll see. Now, slow down, I'm going too fast. If I multiply both sides here by probability of E, this equation becomes probability of E and F, or F and E, same thing, equals probability of F given E times probability of E. Or you put the probability of E first. So this is dependent events. This one is dependent events. And if we look at our independent events one that we had just last week, we had probability of E and F equals probability of E times probability of F. So they look really close to each other. In fact, this gives us a really good test for independence. If the probability of F given E equals probability of F, then E and F are independent events. If this scenario happens, F given E, if it has the same probability as F, it means E happening didn't affect the probability of F happening. Does that make sense? E happening is supposed to, for a dependent event, affect F, but if it doesn't, if it still equals just the probability of F, whether or not E happens or not, it shows that E and F are unrelated. So, let's look at some examples. In 2005, (19.1% of all murder victims were 20 to 24. Also, 16.6% of all murder victims were male 20 to 24-year-olds. What is the probability that a randomly selected murder victim we'll say 20 to 24-year-old murder victim was male? Give you a second to write that down and we'll translate it. Okay, so the first piece of information, that first sentence, sentence one, tells us the probability of being a 20 to 24-year-old murder victim, I'll abbreviate as MB, is 19.1%. As a decimal, it's 0.191. That's 19.1%. Sentence number two tells us the probability of someone being a murder victim that was male and 20 to 24 years old. So this is probably being a male and 20 to 24-year-old MB. And they gave that as 16.6%. We move the decimal left twice and we get 0.166. Next, they say, what is the probability that a randomly selected 20 to 24-year-old murder victim? So we are working with (20 to 24) and murder victims. That's going to be our given piece of information for our next step. They want to know what the probability of it is being male. Probability of being male given 20 to 24-year-old murder victim. Well, as a quick recap, we're doing probability of F given E equals probability of F and E over probability of E. That's our formula. So it looks like my male is the F part and the 20 to 24-year-old is the E part. So I need, this is probability of male and 20 to 24-year-old MB divided by probability of 20 to 24-year-old MB. Is 0.166 divided by 0.191. And I am getting 0.869 or 86.9%. If they found a murder victim that was 20 to 24 years old, there was basically an 87% chance it was a male. This kind of makes sense to me. People that go around killing each other, men tend to get in more fights with men than women do with women. So like that, like same-sex murder is like higher for men. And then let's look at like opposite sex murder. Like men that kill women isn't as many. Like men will be abusive to women. This is fucked up. They'll be abusive to women, but they don't kill them. In general, women though, like if you fucking push them enough, you fucking are abusive to them enough, you're waking up with a fucking knife in your neck. You know, like I've done had enough. I can't take you all out when you're awake and you can fight back and hurt me. So I'm gonna take you out while you're sleeping. Or I'm gonna fucking slip something in your food or your drink, something like that. I'm gonna, you know, just for my own goddamn safety. So more women kill men than men kill women, and then more men kill men than women kill women. All around, men just get killed more often than women. It seems like this should be true for any age bracket, but they have the percentages for 20 to 24-year-old. Here, we weren't given the number of people that were chosen in each group. So I can't do the second half. I can't do this N1 here, but we'll do the N1 on the next one. I do want to point out what happens if you do this upside down. What happens if you put the numbers in wrong? And what I mean by that is putting the 0.191 on top over the 0.166. You should get 1.151 to 3 decimal places. And that's the probability of male given the murder victim one. Is there anything wrong with the probability being 1.151? Say that again? Yeah, if we look at this as a percentage, shift that decimal point twice, that's 115.1%. There is no way that more men were murdered in that bracket than total number of people murdered. That's not possible. Probability for anything has to be between 0 and 1. So if you put it in wrong, you're more than likely going to get an answer that doesn't work. And if you just keep in mind, think of it just as a percentage. Shift it to a percentage, go, is this a realistic percentage? Yeah, I know there's assets that say I give it 110%. No one gives it 110%. You can only give it 100% or less. Like when they say I'm giving it 110%, they really mean I fucking give everything else like 80%, but I'm going to give your shit at least 90%. It's not even 100% usually. Someone that says I give 110%, they're not giving it their all. They're giving it almost their all. If you want something to happen as much as you want to breathe, then you're giving it your all. And that's very few things in life. In fact, I can't think of many. Can anyone think of anything they would rather do? They want to do as much as breathe? Just has anyone ever been like fucking stuck underwater and like when you're playing the swimming game and someone holds you down and you fucking start to panic and start holding you down too long? There's nothing you want more than fucking oxygen, and you're willing to fucking hurt whoever's holding you down. If you had a knife, you'd fucking stick them if you thought it was a serious enough threat. All right, so that's one example. There's very few things that I'm willing to fucking stab someone for. I'm getting in trouble. I'm not a good enough criminal. Let's take a look at a situation where we have numbers, not probabilities. A survey was conducted about faith. Yeah, I'm bringing in religion. Imagine that. This was done in 4 different regions of the US. I don't know how they decided these regions because they doesn't seem like fucking good regions. But we had East, West, South, and then like Midwest. Feels to me like North should be the fucking 4th group. But they're like, nope, middle of the country. The Midwest is really just the middle of the fucking country. I don't know why they call it Midwest. It's just the middle. This is your good old fucking Kentucky and the Bible Belt stretch. That's your middle. And that was, so these are the regions it's done in. And they asked, are you an atheist? Do you believe in God? Or is there some universal spirit? Maybe not an almighty, but some like Mother Nature is a universal spirit. You worship the earth, Mother Nature. That's not a god, but so to speak. But there are people that worship the earth. Seems like a good thing to me. It's fucking there. You're standing on it all the time. It feeds you. Of all the things to worship, I think Mother Earth would be, if I chose one to worship, it would be Mother Earth. So here's the results based on region. It's going to be a table. How long I wrote, how many rows I need. I got East, I got Midwest, I got South, and I got West. So it looks like I need longer columns. Maybe I'll put a little dotted line between the middle of the two so it's easier to see which one's which. We have 204 here, 212 here, 219 here, and 152 here. 36 here, 29 here, 26 here, and 76 here. 15 here, 13 here, 9 here, and 26 here. I don't know when this poll was done. And I don't know. So I can't tell you how long ago this was. It's been a while. So if we do some quick tallies, just like totals here, we might want these in a second. So I'm going to put them down. This is 787. This is 167, and this is 63, for a total of 1,017. I guess we could add sideways. This is 255, 225, and 29 is 254. 219 and 26 is 245, plus another 9 is 254. And 76 and 26 is 102, added to 152 is 254. So about the same number of people each region. That's what it looks like they were going for. Seems like a weird number to pick. So we will use this. I'll let you finish writing down. And we're going to use this table to figure out a couple different probabilities. Okay. Our two questions are going to be, well, I'll do one question first. What is the probability that someone who will be lives in the West is an atheist? I should say someone. Someone. And the other one we're going to look at in a second is probably that someone who is an atheist lives in the West. Those questions look very similar, right? They even have the exact same words, just in a different order. They mean two different things. The question part here is this is our question part here. Like this is the part we want to like break it down by. And so like what comes before that is going to be our given information. So the way to read A is the given pieces lives in the West. That's what comes second. Oh, that should be a P there. The probability that someone is an atheist given that they live in the West. So this will be A. This scenario is really handy if we do, both of them have both setups will have atheist and West over just West. And we can either do N or we can do P, but we already have N. N is going to be quicker. Looking at the table, can anyone tell me the number of people that are both atheists and live in the West? It's 26, right? What about the number of people that live in the West? 254. That'll be our probability. That's our answer. So like lives in the West, what you're basically doing is blocking out all the other shit you don't need. We don't need anything up here. We just need this row for the West. And we're looking at this information right here. 26 out of 254. If we do the probability formula real quick, the one with the probability of atheists in West, over the probability of West. Atheists in West is 26 out of 1,017. The probability of West is 254 out of 1,017. Here we got fractions inside of fractions. These two are equivalent, but I think the first one's easier to work with. Here you could go to a decimal. So two approaches if you do this way. Option one, do decimals for top and bottom first. Then the big fraction. Or option two, you can multiply by the reciprocal. This requires remembering how to do a little bit of math. You multiply the bottom fraction by its upside down part, and you do that on top too. This ends up being 1 on bottom, and this ends up being 26 over 254 on top, which is just 26 over 254. And if you put this in a calculator, we get 0.102. 10.2%. Now, I don't know about you, but that's a lot of tedious shit. When all I had to do was get the totals and jump straight to simple, easy peasy in the calculator. No chance of having different shit going on. I think it's much easier that way. This works when you have all the numbers rather than a probability. If you already have the probability, this part's easy anyways. You just put them in a fraction. Like we did in the last problem with the murder victims. All right, with that piece of information, what about probability that someone lives in the West, given that they are an atheist? So the formula is probability of both West and atheist over the probability of just atheist. Or instead of doing probability, let's do n. We already said that was the easier approach. Let's do n. We already did number of West and atheists. That was 26, right? What is number of atheists? 63. So this is about 0.413 or 41.3%. Looks like there's a higher percentage of atheists that live in the West than in other places. We're a bunch of heathens out here, right? We're all going to hell. Not all of us. Some of us. Or whatever version of hell your religion, bad place. Most religions have a bad place. The bad one is called Bad Place. Have you guys seen that TV show, The Good Place?
Yes.
It's pretty fucking good. The first season, like if you haven't watched it, like I think four people get into heaven, and you learn relative, like it is like heaven is like a little tiny community, and everybody's all happy and jolly, and there's fucking like unlimited ice cream and shit like that. And the four people know they don't belong there. And they're trying to fucking fit in and act like they belong there. It's pretty good. I don't want to say anything more about it because it will ruin the entire like plot, but that's just like the premise. It's got Ted Danson in it. It's got who's that pretty blonde? Kirsten. I gotta look her up. It's Kirsten something. All right. That's kind of it for 5.4. So our recap of equations right now is, does anyone need this longer before I start yanking it? So our general addition rule, we had probability of E. Oops. Fuck it. Let's just tear that shit up. Start with a nice, fresh, clean piece of paper. Fuck up right away, just scratch it. Probability of E or F equals probability of E plus probability of F minus the probability of both. No, like that was like, I don't know, 5.1 or 5.2 or some shit like that.
Yeah.
General, that was, I'm just summarizing the equations we've gotten so far. So that was our general addition rule. It's handy to note that the or turns into the plus. Another way of writing this is probability of E union F. I don't tend to use that because I think or is just as good as saying the other one, and then they'll have intersection F there. But like mathematicians wrote this shit and they like to fucking put as much confusing shit in there as possible. Am I right? Like, let's fucking make it complicated. So that was our general addition rule. Then we had probability of E and F. Had two outcomes. It was either probability of E times the probability of F, or probability of E times the probability of F given E. And this was for independent events. And this one was for dependent events. In both cases, you'll see the and turns to multiplication. So three main formulas right now. I would really like ignore this one right here. I'm gonna kind of like put a line through it. Fuck using union and intersection. I'm a fucking rebel. I know how to do or and. Like that makes more sense. You say it in a sentence. E union F doesn't make any sense. E or F makes sense. All right. 5.5. Does anyone want like a 5-minute break? If you want to go to the bathroom, just like raise your hand and then go. We'll take a break. Anybody? All right. You want to go? Okay. Kirsten Bell. Thanks, Brittany. It is Kirsten Bell. Let's start 5.5. Five point five is on counting techniques. In my head, I think this should be done like before 5 point, the rest of them. So like, let's just start with an example. A typical California license plate. Starts off with a number, followed by 3 letters, followed by 3 numbers. So that means it's a number, and L means letter, like letter of the alphabet. We're going to assume there's no other symbols and shit like that. Well, we don't even need that for what we're doing. How many combinations can we make? Like how many different, like basically how many different plates? How many options does the first character have, that number? What? Not 9, it's close to 9. 0 is an option 2. 10. Letters, hopefully you all know there's 26 of them. And like license plate can have repeat characters. So like the next one can be 26 and the next one can be 26. And any of the last 3 ones can be anywhere between 0 and 9. If you multiply that out, that is 28,624,000. That's a lot. Nope, that is not the number. That's the different number. That is even a larger number, 175,760,000. That's me jumping ahead on my notes. So like having the probability of a very specific plate, like 1 A, B, C, 2, 3, 4. There's only one plate like it out of 175,000 or 1,760,000. I'm going to leave it like that. I don't need to turn it to a decimal. It seems like it's a pretty fucking low number, though, right? It's like you're less likely to have a specific license plate than win the lotto. Like that kind of unlikely. All right, so what if we restrict it? What about if there's no repeat characters? Well, the first number can be 0 through 9, so it can be any of them. It can be 10. The first letter can be any of the 26 letters. Let's say we pick D. How many letters do I have to choose from for the second character? 25. It's 1 less, right? What about the third character? Or third letter is 24. What about when we get to the second number? 9, and the third number will be 8, and the fourth number will be 7. This is where you get the 28 million I was giving you earlier. So there's a lot less combinations. These ideas, these are related to this either setup is called the multiplication rule of accounting, or not accounting, of counting. I think this is helpful to know. Maybe in the future I'm going to teach this before I do like 5.2, because like if we have 2 dice, a red box, a red cube, and a green cube, each one has 6 sides. So any combination, there are 36 ways those dice can be rolled. And all of our probabilities for dice have a denominator of 36. So anytime you do a probability with using dice, it's or the sum of 2 dice, it's over 36. It comes from the same thing. I think it might be easier to do this first. Maybe I will in the future. Like this applies to other things. If you have options for anything you do, let's say you go on a cruise. Has anybody been on a cruise? Been on one. They generally like do whatever you want, and you can have like one sit down dinner in like a fancy restaurant. Maybe more if you pay for more. I don't know. We only paid for one. But like we were doing, like you're on a boat. They don't have unlimited choices. So like for a dinner menu, in fact, Chili's does this all like pick your pick two or dinner for two. You have only so many choices. You have P choices, different choices for your appetizers. You can pick one appetizer out of so many different appetizers. Then maybe Q for the different number of entrees. Chili's, I think, has maybe 6 or 7 entrees you can pick from. Each person can pick a different entree. And then like there's desserts. You can pick one from the desserts. And so the total number of combinations here, total different meals that can be made is P times Q times R. All right. Next step, I need to cover factorials with you before we do the next thing. Factorials have an exclamation point. I think the easiest way to show you what a factorial is just give an example. 5 factorial means 5 times 4 times 3 times 2 times 1. Is the pattern self-apparent? You keep multiplying by a decreasing number until you get down to 1. So 6 factorial would just have one more number. So you could write 6 factorial as 6 times 5 factorial, for example. The only difference is 0 factorial. 0 factorial, I can't count downwards to 1. 0 factorial equals 1. It's defined this way. It doesn't follow the pattern. It's completely opposed to the pattern. Like anything times 0 should be 0. Yeah.
So what about 1 factorial?
1 factorial is just 1.
So 0 and 1.
In terms of factorials. The reason why is there is a point, they just use this exclamation point to show a shorthand way of doing it. But where in the cases we use it, 0 factorial just means there wasn't any choices, but there's only one choice. There's no options. That's a better way of saying it. There's no other options. So you only have one way of doing it. You'll see where they come up in a second. Most calculators have this in there's 2 different formats. You'll see this on a calculator. On calculators, you will see x factorial like that. So to get what I wanted, I would hit 5 and then I would hit x factorial and then I would hit equal. And it would spit out 120. Which is 5 times 4 times 3 times 2 times 1. The other option is calculators that have the PRB button. If your calculator has a PRB button, when you hit it, 3 things will appear. You have n factorial, you have NCR, and you have NPR. In fact, we will be covering all 3 of these today. They are all related. That's your factorial. This is called combinations or combinatorics. And this one is for permutations. Most calculators that have the x factorial have an equivalent of this, but it's usually like there's a shift key and alpha, like you gotta hit one button and do like, hit another button and it'll do like access a different function. That's how my calculator is. In fact, my calculator, you can't see it, but above this key, the x minus 1 key, let me see if I can lift it up. But it does not fucking show very well, does it? Fuck it. Above that key, if I hit this key and then that key, I get the factorial. I have NCR listed. And then if I hit the shift key and that key, I get the NPR. We need to know how the factorials work for discussing permutations and combinations, which is most of the rest of the talk. So I'll give you a second to finish writing that down and then we'll turn the page and start going over permutations. All right. Does anyone need that longer before I start yanking it? All right. So I said we had NPR and we had NCR. This is permutations versus combinations. Permutations versus combinations. P and the C are both for the name of what we're doing. P, C. The N is the total number of total objects to choose from. R is the number to be chosen. Or number selected. This will make more sense when I do the setup here. Combinations, I think the easiest way to think of this is think of a combination pizza. Doesn't matter what order we put the toppings on, if we're gonna throw it in the fucking oven and cook it. Like other than you generally want the sauce layered first, but that's not really a topping. A lot of places put cheese next, but that's not necessarily a requirement either. You could put cheese last. You got pepperoni, you got bell peppers, you got onions, you got shit like that. It doesn't matter which topping you put down first. The order of the toppings doesn't matter. So that's what goes with C, combinations. Permutations. Order does matter. That's the real big difference between this. Like, if there's a first, second, and third place. What position do you want to be in? First. Hopefully. Hopefully you want to be the first place. Because let's face it, second place is just another loser. Second place is the first place loser. Right? You still lost, you didn't win. Give him a second. So order does matter. It's kind of interesting. It actually has the letters for matter in it. M-A-T-T-E-R. I don't think that's the easy way to remember it. But it was something, a fun observation the student made one time. I think doing the combination pizza makes sense. The order does, the order doesn't matter on that one. So permutation is the other one, order does matter. So like for that we could do first, second, third place. Like if you're picking officers for a club, you might have president, vice president, treasurer, secretary. Like order kind of matters. Let's look at the equation for, let's work with permutations first. We'll come back to combinations. Permutations, it has the formula NPR. And this is n factorial over parentheses n minus r factorial. Let me give you an example. Trifecta. If you go to races, like the horse races, this is true story, happened to me. I don't know how young I was. It was like 10 or 11 or some shit like that. I grew up in Sacramento. We had not a county fair like Larry does. We had the state fair. All the county fairs came up there, brought their shit up, showed their exhibits there. But it was at Cal Expo and there was a racetrack there. And my friend's dad fed the horses, so we got in free. And my cousin took me, and my mom had to work during the day. My cousin didn't. She was older than us. She took me and my brother. We were maybe like 10 or 11. And mom gave my cousin some money to like, let's have some fun at the fair. And she wanted to show us how bad horse racing was. So the trifecta is you have to pick first place and second place and third place in order. If you pick the right 3 horses, but the wrong order, you lose. It's a hard fucking thing to win. It's got a very low probability of hitting, so the payout is high. So she had us play the trifecta. Me and my brother did 1 ticket. She bought her ticket for us out of our money, was trying to show us gambling's bad. I won. I knew nothing about horses. I picked based on the names that I liked, and I won. And that bitch didn't let me spend my money at the fair. That defeated the purpose of the lesson. She went home and gave the money to my mom. I got to spend everything else that was left over from the money. Her argument was, your brother has less money to spend. I want you guys to have the same amount of money to spend at the fair. I think that's bullshit. She was trying to like either like show that it was bad, or I don't know, she might have scammed my mom, gave my mom less money than I want. I have no idea. I'm going to assume she gave her the full amount. You never know. But this is the trifecta. Horse races have, let's say there was 12 horses. That is our N. I had to pick 3 horses. Or anyone that plays a trifecta picks 3 horses. That's my R, the number to be chosen. So my NPR in this case is 12P3. In fact, that is what I would type into a calculator. I would hit 12, I would do the NPR button, and then I would do 3. But this formula is actually pretty easy. I can actually do this one by hand. This is, N is 12, that's my first number, that's what's on top. And it's a factorial. This one is N minus R, so 12 minus 3, and then factorial. So 12 minus 3 is 9. If I wrote those out, that is 12 times 11 times 10 times 9 times 8 times 7 times 6 times 4, 5, 4, 3, 2, and 1. All over 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Almost all that shit cancels out. The shorter way of writing this is 12 times 11 times 10 times 9 factorial over 9 factorial. All this shit cancels out down here. That cancels out right there. You're left with 12 times 11 times 10, which is 1,320. There are 1,320 ways to pick the trifecta if there are 12 horses. I don't remember if they had 12 horses. I'm giving an example. I want to say it was 12, might have been 10. So my probability of winning the trifecta, if it was 12 horses, there was only one winning ticket or one winning combination out of 1,320 combinations, which is 0.000. Is that too many zeros? Nope, 3 zeros, 7, 5, and it just keeps alternating 7, 5. It's repeating there. So less than 0.07% chance of doing it. And she didn't even let me spend any extra fucking money. That bitch.
How much was it?
I don't remember. I was young. I'm sure it was in like in the $100 range. They were $2 tickets. So like it was over 50-1 odds. Generally, there are I didn't know anything about horses, but there are horses, like if you follow horses and you're good at looking at like horse flesh, they call it, looking at the horse flesh. Like you can see which ones have like deeper lungs, have more stamina, stronger muscles. You can get a good idea of who's gonna be a contender for the tops. Now getting the actual order right isn't as easy. So that's why they don't pay 1,000 to 1. It's only like 50-1 or some shit like that, 100 to 1 maybe. That's NPR. I will show you me doing this in a calculator. My NPR is above my NCR. I'm gonna do 12. Shift and I hit it and mine shows a P on the screen. And then I hit 3. And it gives me the 1,320. So you can do this on the calculator, and or if you don't have a calculator, like this is if you don't have a calculator that does factorials. If you've got like every once in a while, a student will bring in like a calculator that all it is the 10 numbers and then multiply, divide, add, subtract, equal. And a decimal point, there's a decimal point in there somewhere. And they're generally, for some reason, these calculators that have very few buttons, they're always like the fucking biggest calculators in the goddamn world. They were made like 50 fucking years ago. They still work. They're unbelievably good at what they do. That's NPR. Order matters. Let's take a look. Does anyone need that up longer? Let's take a look at combinations. Combinations, order doesn't matter. It looks very similar to NPR. We have n factorial on top. We have n minus r factorial on bottom. We also have r factorial on bottom. So it's got a little bit more. This button or this option is used so much, they shorten it to saying n choose r. They don't say n combination r, it's just shortened to n choose r. You have n objects, you choose r objects. N choose r. Here's an example you all get. Let's see how many people we got in here. We got 5, 8, 9, 10, 11, 9, 10, 11, 12, 16. Holy shit, an entire full row. 21, 22, 23, 23 people in here. Let's say we've got, okay, this is our example. We've got 23 people in here. Students in class today, present in person. What if I say 3 of you are getting an A no matter what? Getting a guaranteed A no matter what you did on the test. Getting guaranteed A. Who in here wants a guaranteed A? This isn't a trick question. I'm only seeing like a couple hands up. A lot of you. Some of you might be too busy writing down. Some of you might want to actually earn the A. You can get a guaranteed A to still earn the A. But like if you were new, you were getting a guaranteed A. The chances of you putting in the work to get a guarantee, get the A anyways, are probably slim. I personally would not rather have the guaranteed A. I'd rather earn it. That way I knew I knew the material. But no judgment. I'm picking 3 fucking people. And you want to be one of them. Do you give a shit if I choose you to be the first person selected or the third person selected? No, the prize is the same. So it's this kind of scenario that you're looking for and choose R. This kind of scenario would be and choose R, which is 23 choose 3. Which is 23 factorial over 23 minus 3 factorial times 3 factorial. And so that's 20 factorial there. I'm going to do that same expanding thing I did earlier with the other one. I'm going to do the top one down until I get to the factorial on bottom. I've got a 20 factorial on bottom. I'm going to do the 20 factorial on bottom. I've got the 20 factorial there. I will write out the 3 factorial though. That's 3 times 2 times 1. The 20 will cancel out with this one. 2 goes into 22 11 times. And 3 goes into 21 7 times. This is 23 times 11 times 7. If I have a basic calculator, I get 1,771. That's just doing it that way. If I choose to do 23 NCR 3, I also get 1,771.
How did you get the percent of it?
The 22 and the 2, I cancel out a 2 to get the 11. And 21 divided by 3 is 7. Or at this point, you could have just done 23 times 22 times 21. Oops, I did times 11. Divided by 3, divided by 2. So you didn't need to cancel like I did. Point is, you could do this in a calculator. But I'll write that over here. If I didn't simplify, it's 23 times 22 times 21 over 3 times 2. You do that in a calculator, you're going to get the same thing for any of these combinations in the calculator. Is ready for more? You can calculate the probability of winning the lotto this way. Let's say you're doing the Mega Millions. I think Mega Millions is out of 70 balls. Does anyone know? I think it's pick 5 out of 70. And then 1 out of 25 for the Mega. So the number of combinations. I'm gonna call it X for a second. Is 70 choose 5 times 25 choose 1. And the probability of winning, whatever that number is 1 over the value X. You will find, just as a quick note, N choose 1 for anything is just N. There's a shorthand notation for that. And you'll also find, as you're going to see in a second, N choose N is just 1. If you're picking 5 objects, there's 5 objects to pick from, and you pick all 5 objects, there's only one way to pick them. You got to pick them all. You don't need to memorize those. That's just speeds up doing shit if you do. All right. So last week, I think I'm pretty sure it was last week. We talked about, I don't remember how many, it was pick 4 girls out of, or not, pick 4 people out of, I think I said 15 boys, 4 girls. Not 4 girls, 8 girls, something like that. 15 boys, 8 girls. We're gonna use 15 boys, 8 girls, but I don't know what I said last time. We're gonna use this, and it was, what is the probability that at least one is a girl? And I said we would solve it later. This was under the complement section. So the number of different outcomes in our sample set, we can pick 0 girls, 1 girl, 2 girls, 3 girls, or 4 girls. And we're going to call event E picking at least 1. So E is comprised of 1, 2, 3, or 4. At least 1 means more than that. And we said E complement is the other outcomes. The only other outcome is 0. And we had probability of E was 1 minus probability of E complement. This means E complement is all boys. No girls, all boys, because it's 0 girls. So E complement, these are related. The first one we could pick 15 boys, and there's 23 people remaining. So that's the number of ways we could choose it. Then for the second child, we have 14 boys left. There's 22 people left. Then there's 13 boys out of 21 people left. Then there's 12 boys out of 20 left. So probability of E is doing 1 minus that. Fifteen times 14 times 13 times 12. I have 1 minus. On top is 32,760. Bottom is 212,520. So I have 1 minus 0.154 equals 0.846. There is a shorter way of doing this with using n choose r. Rather than doing all that, this is 1 minus 15. There's 15 boys. We're choosing 4 of them. And the total number of combinations is 23 people. We're choosing 4 of them. So this is 1 minus total number of boys chosen. Total number of boys combinations over total number of any combination. Fifteen choose 4 over 23 choose 4. You'll see you get this 0.154. One more topic. I think I could get it done in 7 minutes. 6 minutes. In this case, everything we've done so far, the objects have been distinct. The boys are each different names, they're individual boys. They're not like just fucking robot boys. We picked horses, each horse was a different horse. What about non-distinct objects? Where they all look the same? How many ways to arrange five white flags, 3 blue, and 2 red. So I could put a white flag here, I could put a white flag over here, I could put 2 in a row, I could have 1 here, I could have 1 here. Let's say that's what I do. For the white, I had 10 spots to choose from, and I chose 5 of them. Then I do my blue flags. How many spots do I have left? I've got 1, 2, 3, 4, 5 spots left. And I'm gonna put in 3 blues. Let's throw a blue there. Fuck it. First 2 are gonna be blue, and that one's gonna be a blue. I had 5 spots to choose blues, and I only chose 3 spots. Out of 5 spots, I chose 3. Red, I've got 2 red flags, and I've only got 2 spots left. Red is 2, choose 2. Now, the multiplication rule of counting says I should be able to multiply these. So 10 choose 5 times 5 choose 3 times 2 choose 2. This is 10 factorial over 10 minus 5 factorial times 5 factorial. Then I've got 5 factorial over 5 minus 3 factorial times 3 factorial. And then I have 2 factorial over 2 minus 2 factorial times 2 factorial. So this is a 5 factorial right here. That's a 2 factorial right there. And that's a 0 factorial there. Notice what happens when I cancel stuff. Those 2 cancel out. Those 2 cancel out. I'm left with 10 factorial on top. I have a 5 factorial, a 3 factorial, and a 2 factorial. And a 0 factorial, but 0 factorial is 1. And we don't need it. It doesn't do anything. Ten was the total number of flags. 5 white, 3 blue, 2 red, 10 total flags. And 5, 3, and 2 are each of the total number of flags for each group. So if you have 10 total objects or n total objects, with k groups, they write this as n factorial over n1 factorial, n2 factorial, nk factorial. Where each of the bottom ones is the factorial for the number for each individual group. Or you could do what I did up here and just slowly calculate it out. That covers chapter 5. And 12, that's me. That's a little fast, right? 5.5 is there's a lot going on in there. Good. You too.